Acid base, lesson number 15, calculations involving Kb. Recall when a weak acid is put into water, the base does not completely ionize. All weak bases undergo less than 100% ionization in aqueous solution. For example 1, what is the pH of a 0.25 molar solution of NaHCOO? Let's begin by writing the equation for the predominant equilibrium. NaHCOO is a salt, and will first undergo dissociation. We're told that we have a 0.25 molar solution. Therefore, the molarity of the Na plus and the molarity of the HCOO minus are both equal to 0.25 molar. Check for spectators reveals that Na plus is an alkali metal ion and therefore can be identified as a spectator ion. HCOO minus is not a spectator ion. It is found on the base side of our Bronsted-Lowry acid base table and can be identified as a weak base. Because it is a weak base, we can write a Bronsted-Lowry equilibrium and just like weak acids, weak bases will be solved by using an ice table. We know the molarity of HCOO minus initially is 0.25. We'll leave out the units, 0 and 0. We don't know the shift here. Well, the shift will be according to Le Chataille's principle from left to right, but the amount is unknown, so we'll bring in a variable of x, 0.25 minus x, and x. Since this is a weak base, we'll have to create a Kb expression here. The Kb expression is HCOOH, products over reactants, OH minus over HCOO minus. We cannot look up the Kb from our Bronsted-Lowry acid base table because we are only given Ka values. Therefore, we have to first calculate the Kb for HCOO minus, which is equal to Kw over the Ka for its conjugate acid. And we can look up the Ka for the conjugate acid from our Bronsted-Lowry table. And we can see that the Ka for HCOOH is equal to 1.8 times 10 to the negative 4. And solving for the Kb, we find that it's equal to 5.6 times 10 to the minus 11. Now let's bring this into our Kb expression. And we'll substitute all of our variables in. In this equation here, similarly to what we saw in the previous lesson in Ka, this will yield a quadratic equation, which we are not expected to solve. Therefore, to simplify this quadratic equation, let's go back to our ice table. We are going to assume that x is very small, and therefore 0.25 minus x is approximately just equal to 0.25, considering x will be negligible. Bringing this back to our question here, this will simplify to x and x divided by just 0.25, and going ahead and solving for x to 2 sig figs, x works out to 3.7 times 10 to the negative 6. Going back to our ice table, we've now solved for x, and x is equal to the molarity of the hydroxide anion. So the molarity of OH minus is equal to 3.7 times 10 to the negative 6 molar. We can solve for the POH, which is equal to negative log of the hydroxide anion concentration. And our POH will work out to 5.43 to 2 sig figs. And therefore our pH would be equal to 14 minus 5.43, and this would be equal to a pH of 8.57. And here is our pH of a 0.25 molar solution of NaHCOO. For example 2, we're asked what molarity of sodium fluoride is required to produce a solution with a pH of 8.50. We'll first recognize that sodium fluoride is a salt. So we'll begin by writing the equation for the predominant equilibrium. The equilibrium does not take place right away. We first have to dissociate the salt. And we're asked for the molarity of sodium fluoride here. We see that sodium is an alkali metal ion, therefore it will be labeled our spectator ion. F minus is a weak base. The equation for the predominant equilibrium begins with our weak base F minus. Because we have a weak base, we'll need to set up and solve an ice table. We don't know the molarity of the NaF or the F minus, so this is where our variable will go. And once we solve for F minus, we can work backwards to find the molarity of NaF. Initially, we have 0 and 0. We're told that the pH in the question here is equal to 8.50. So, if our pH is equal to 8.50, our pOH would be equal to 14 minus that. And solving for pOH, it's equal to 5.50. And our hydroxide ion concentration will be 10 to the minus 5.50. And this will work out to 3.2 times 10 to the negative 6 molar. We'll bring this into our ice table here. 3.2 times 10 to the negative 6 plus 3.2 times 10 to the negative 6. And let's complete our ice table. And now with our completed ice table, we can create our Kb expression, which will be equal to HF OH minus divided by F minus. We'll need to solve for the Kb for F minus, which is not given on our table, which will be equal to the Kw divided by the Ka for the conjugate acid HF. Kw, 1.0 times 10 to the negative 14. The Ka for HF is 3.5 times 10 to the negative 4. We can find that on our Bronsted-Lowry acid base table. This works out to 2.9 times 10 to the negative 11. Now let's substitute everything into our Kb expression. 2.9 times 10 to the negative 11 is equal to 3.2 times 10 to the negative 6. 3.2 times 10 to the negative 6. X minus 3.2 times 10 to the negative 6. And now we have a mathematical expression where we can go ahead and solve for X. This will yield 2.9 times 10 to the negative 11x minus 9.3 times 10 to the negative 17 equal to 1.0 times 10 to the negative 11 plus 9.3 times 10 to the negative 17 to both sides. This will yield 2.9 times 10 to the negative 11x is equal to 1.0 times 10 to the negative 11 divided by 2.9 times 10 to the negative 11 to both sides. We find that x to 2 sig figs will be equal to 0.35. Going back to our ice table, we defined X as the initial concentration of F minus. So the concentration of F minus is equal to 0.35 molar. And if we go back here, if we see that the molarity of F minus is 0.35 molar, the molarity of NaF would also be 0.35 molar. It's a 1-to-1 mole ratio going across the dissociation of the salt. Therefore, the molarity of NaF initially is also 0.35 molar, and there's our answer to this question here. The Hebden assignment for this lesson is pages 153 to 154, numbers 84 to 93.